Today. When's homework due?
Tomorrow.
Go team, here we go. Linear functions, characteristics. First of all, what are the different equations of lines? What do we got? Absolute.
What?
Standard form, ax plus by equals c. That's great. What else? Slope-intercept form, which would be y equals mx plus b, and the one that I don't want you forgetting, but you probably like the least, which is y minus y1 equals times
X minus X1.
Can't even say it slow. Okay, so we have our three equations of lines. What else is exciting? What's the domain and range of most lines? Ooh, I just got excited. Domain, all real numbers. How will we write that in interval notation? How far left is all real numbers? How far right? So it's from? Got it. What would the range be for most lines? All real numbers, hence the interval would be? Now, what is the exception, or what are the exceptions to that domain, that range? True, but not for lines though. Which lines are exceptions? There are, like, we have to be careful, denominators and square roots, but those won't be linear. What lines don't have domains of all real numbers? Not equality, so those won't be lines either. Did you hear it over there on the side?
Constant.
Constant. Constant would be the exception for this one. Why would the range not be all real numbers for a constant function? What's the range? Just C, right? Because horizontal, you can't go up or down, it's just one y value. So the exception for range is a horizontal line because there's only one y value, that's it. And then you guys already kind of figured out what's the exception for the domain being all real numbers? What's the equation of the vertical line again? It's not y equals. And the domain of a vertical line would just be at C, right? Oh, we used up our three lines. Anything else? Domain, range. Could be strictly increasing, could be strictly decreasing, could be strictly constant. We'll say that every line only has one behavior. It's either going up, or it's going down, or it's staying constant. I think that's good enough. Special lines, we already talked about vertical, that's x equals c. Horizontal, that's y equals c. We already talked about the exceptions of those two special lines. I guess you can graph it if you really, really want to, but otherwise we're good. The constant function, some of you guys couldn't see it, it is f of x equals c, or y equals c. Identity function, when x is 1, y is 1. When x is 2, y is 2. Pretend those points are on the line. When x is -1, y is -1. Y equals x. He's super important for lots of reasons. But we'll talk more about him another day with inverse functions. But not today. You guys have it? Going once, twice, and ooh, squaring functions. Hey, this is the section where we talk about all the parent functions. Isn't that the title? Yay. So all the basic non-transform. Ooh, guess what's coming? Transformation. But first the basic ones. Quadratic, what do we know? Yeah. It is a parabola. It does have a vertex. And if it's a concave up parabola, that vertex will be positive. The coefficient will be positive, but the vertex will be a low point, aka snazzily called a minimum. So we can talk about a few basic transformations, but once again, this isn't exactly the transformation part. We're just talking about the basic functions. So we will talk about characteristics that are parabolic in nature. So they are going to have, in a sense, two different branches. And what I mean by branches are two different behaviors in the sense that it's going to be decreasing, the parabola decreasing and then increasing, or it was reflected, it would be increasing and then decreasing. So it doesn't have a strict behavior like a line. It is going to change behavior at its vertex. We can talk about just a few super basic forms. Since we did talk about y equals mx plus b, there were some transformations done to those lines. So we'll talk about the equations really quickly. But I bet these equations will come back up again. What's standard form of a quadratic? Standard form of a transformed quadratic. There is an x squared, but what else could there be if it's transformed? There you go. Quadratic formula, right? Comes from ax squared plus bx plus c. That's standard form of a parabola. There is another form that you might see. There are different ways of writing it. I'll write it this way for now. It's called vertex form. In some books, it could also be called standard form. In other books, I think our book calls it standard because it's so important. Let's see, what else could show up with quadratics? How many zeros could a quadratic have, depending on where it's placed? 4. 4. None. So it could have, there's possibilities of having 0, 1, or 2. Depends on where the parabola is placed, right? But how do we find those zeros? With lines, it's just like, use algebra, solve, no big deal. Set it all equal to 0 and solve. But with quadratics, what do we have to be careful of when solving for zeros? What am I going to fill in? Solve with what? We practiced it the other day. There's the guess and check. There's the X method. There's grouping. Factoring does work, but what else will work with quadratics for finding zeros? X equals negative b. Oh yeah, graphing. That's true. Plus or minus squared. B squared minus 4.
Missing one time and we have to sing again.
Yeah. These are one-time only coming up. Gotta pay attention else you miss it. Kind of his humor. And his love for structures. Okay. I think that's good enough for quadratics. Sound good to you guys? Could be concave up, could be concave down. We'll talk more about the quadratics when we have like transformations to put along with it. Well, let's do one more thing. We talked about the a, x squared, or a in front of x minus h squared. Let's really quickly with that. I'm coming back to what you said. It's going to be concave up when a is positive, right? It's going to be concave down, it meaning the parabola, when a is negative. My question to you, after writing those two down, what's going to happen if a equals 0?
Spacing off.
It's not that it's impossible. A can equal 0, but what's going on if a does equal 0? It's a line. It's not a parabola. There's no squared left. All right, let's keep going. If a equals 0, it's not a parabola anymore. It's a line. Cubic functions. Sadly, cubic functions don't really have a nice word that describes the graph. If you guys can't read because it's too light, it's just y or f of x equals x cubed. Has the points 0, 0, 1, 1. 2 would go to where? For the cubic function? 8. Good. 2 cubed is 8. Negative 1, negative 1, negative 2, negative 8, etc. How many branches does a cubic function have? The parent function at its core has 1, but it can have up to 3. It can have up to 3. Just depends. Because you could have, technically, it's not even gonna be 1 through 3, it's technically gonna be 1 or 3. Because you could have strictly increasing or similarly strictly decreasing, in a sense it's one branch. Or you could have 1, 2, 3, if it was distorted. You could have up to 3 seen branches, visible branches, I should say. Let's see what else. Maximums, minimums. You knew calculus, you could talk about those more, but without calculus, we're kind of stuck on just saying sometimes some maximums and minimums can appear. That's kind of boring. Let's look at cubics. Ooh, they do have a point of inflection. And I'm going to put in parentheses in the center. I don't really like that way of describing it. But they do have a point of inflection at this, or for this parent function. That point of inflection would be at the origin. Oh, that's kind of funny actually. Inflection. Could have an infection too. Poor little guy. Okay, so point of inflection. What is a point of inflection? You guys know or remember? What's changing at this point? Huh? Couldn't hear where it is. Okay, it is the center, but what's changing? Where do you hear the word inflection, like in everyday life? Not that you hear it every day, but in normal conversation. You never heard inflection?
No.
Someone's voice doesn't have any inflection? Okay, let's put it this way. Someone who speaks in a monotone voice doesn't have much inflection. It's a change in the, it could be, I mean, it has something to do with emotion in the sense of like with the voice. If someone has no emotion, they just talk like that, it's really boring. But the point isn't that they don't have emotion. Maybe they're like going all like this and their voice is like this. It means there is no, hey, look, oh my goodness, what's inflection? Change of pitch, that's kind of what it means in terms of voice, but in here, or with the graph, it means change in concavity. Concave down before, concave up after. There's a change in concavity. You can see it a little bit better maybe in this one. Maybe this seems a little bit, to make a little more sense with the voice thing. You have a change in concavity at the point of inflection. Anyway, change in concavity. Or it marks the change in concavity. Because you guys know that to be concave down, you don't have to have a full frown, right? To be concave down, you don't have to have a full frown. This is concave down. Why? Because it makes part of a frown, true? To be concave up, you don't have to have the whole cup. Something that quite a few students kind of have confused before they come to pre-calc. You don't have to have the full cup to make it concave up. You don't have to have the full parabola or the full smile. You just have to have a portion of it. Same thing as concave down. So at the point of inflection is where the concavity changes. I guess we could talk about cubics and zeros. How many zeros could a cubic function have? Could have up to 3. What are other options though? No, it's not going to have 0. You guys see how the end behaviors are opposite? It's going to always cross through. It could have 1. Nope, couldn't have 1. Oh, no, it could. If the axis was right there, right? That'd be 1. Could have 2 if the axis was right there, or it could have 3, right? But can it hit in any more points than 3? So the zeros you're going to have, let me get rid of all those little lines because they're kind of in the way now. You could have 1 or 2 or 3. You have 1 or 2 or 3, just depends. All right, that's enough. Maybe you'll use factoring as well, but whenever you're factoring a cubic for the zeros, you'd have to maybe use synthetic division, maybe long division, maybe something known as the rational root theorem. Let's keep going. Square root function. We're doing well, we're doing well. Square root function. I'm going to give you a second to get down the graph. The parent function is y equals square root of x. Don't worry, it wasn't that bad. I just solved it quickly. Okay, I can write that one. I gave him points on his notes. Which of us have never spilled a drink before? Ever?
Purely.
Yeah, we're human. So.
That's it.
Maybe we should get Kobe those like anti-spill cups.
No, I could set our screen drinking alcohol.
It's not tasty.
Yeah, this is
Right there.
Question: how many concavities does a square root function have? One. One concavity. How many branches? One. Ooh, what's the domain? That's what we forgot about the other two, domain and range. Oh, it's okay, we'll go back. But first of all, how many branches? Just one. Strictly one behavior, either strictly going up or strictly going down. If it's reflected, it might just be going down. If it's normal, it's going up, it's increasing. No points of inflection. It could have a maximum or a minimum, but we'll talk about that with domain. One branch, one concavity. What's this one right now? What concavity is that? Is it part of a frown or part of a smile? That's not a smile, is it?
It's like a
If you finished it, what would it be? Part of a frown, true? So what is it? Concave? Down and frown, good. So its parent function is concave down. If it gets flipped, it will be concave up. What's its domain? Its parent's function's domain. X cannot be negative, hence we would say X is, hey, we already talked about his domain problem. What's underneath must be greater than or equal to 0. We talked about that, yeah? What's his range for the parent function? Greater than or equal to 0 as well. Both domain and range are restricted for a square root function. Let's not really stress about a standard form of the equation. It's not quite like linear or quadratic. So let's go ahead and quickly go back. Sorry, go back. Just for the basic parent function, what's the domain of this guy? All real numbers, good. So we could say from negative infinity to infinity. What's the range? How low, how high? Yeah, it's going to go forever low, forever high. I want you guys to go back to the parabola, back to the parent function, y equals x squared, and what would you answer for its domain and range? Don't say it out loud. Go back to the parabola. What would you answer for its domain and range? Domain, how left does the parabola go? Negative infinity, and how right does it go? Okay, so that's the same, all real numbers. But what's the range?
0.
How low does it go? 0, and how high does it go?
Infinity.
So would that be a parenthesis or a bracket at 0 if I was doing it that way?
Bracket.
Good, just reviewing interval notation just because we can. We can use inequalities, or we can use brackets and parentheses with interval notation. I'll give it a couple seconds. I have a few people still writing it. Domain, all real numbers, negative infinity to infinity. Range, 0 to infinity. So parabolas, well, they do have that low point, remember? Or if you flipped it, it would have a high point. So how low would it go, negative infinity? How high would it go to the y value of the vertex? But cubic functions, well, they'll just keep on going forever. Square roots, they're limited as well in domain and in range. Reciprocal function, he's fun. You guys can't see the equation, it's y equals 1 over x, or f of x equals 1 over x. Y equals 1 over x, or f of x equals 1 over x. Is there anything special going on at x equals 0? On this graph?
Both lines are approaching.
Both sides of the function are approaching? That's a good word. Approaching what?
The y-axis.
Yeah, kind of. True, they're technically approaching the y-axis and the x-axis. I heard the word asymptote and I like it. I probably don't remember the geographies, but geography. The cross country stuff. Started saying asymptote and so I started seeing it. Yes, there are two different asymptotes. Let's first of all talk about the domain. What can x not equal? X cannot equal 0 because of the denominator. And more specifically, what's going on at 0? Remember, vertical line, x equals 0. There's a vertical asymptote. What is the range in this one? Yeah, I agree. Y does not equal what? Good. And what kind of asymptote's going on that horizontal line? You guys okay with the VA and the HA? Vertical asymptote and horizontal asymptote? Just really quickly, because a few students tend to get confused here. This graph doesn't cross the horizontal asymptote, right? Does that mean that no graph can ever cross a horizontal asymptote? Is a graph ever allowed to hit a vertical asymptote?
Yes.
No, because a vertical asymptote comes from a domain error, right? So a vertical asymptote comes from a domain error, comes from a, x cannot equal. Horizontal asymptotes come more from just what's going on as you go this way and as you go that way. It doesn't actually talk about what is or is not allowed to happen. Now, this one graph, once again, y is not equal 0. But my question to you is this a valid graph? Is it impossible or is it possible? This one. It's possible. This is an actual graph function. I actually forget what graph it is right off the top of my head. We saw it in calculus a couple days ago, where there are vertical asymptotes. And the function will not be allowed to hit those vertical asymptotes because they are domain restrictions. The x value would make the function not exist. But just because as you go to the right and as you go to the left, there is a horizontal asymptote, does not mean that the function can't cross it somewhere else. Just wanted to make sure you knew that. This is not a reciprocal function. I mean, it does have a denominator somewhere, but that's not a specific case of this one. This is definitely a more advanced function, but I just wanted to let you know, vertical asymptotes, it cannot cross. The function cannot hit. The x is not allowed to be used at all. Horizontal, it just works differently. It might cross somewhere in between. The point is as you go out, the function gets closer and closer. Let's see what else. How many different concavities? Because this portion would be frowning or smiling apart. Good, concave down. You guys see the concavity, right? Like if you were to finish it, it doesn't finish, but if you were, it'd be a concave down portion. And what would this be? Good, concave up. It's all about the curvature. Talks about our VA, talks about our HA. Technically, I guess you could say there are two different branches. It's all branches. Right now it's just a candy. Okay. Branches. Now it's good. You do have this branch decreasing, this branch. Ooh, they're both decreasing, but we still say two branches because they are separated. But they have the same behavior of decreasing. That's about it. Nothing too exciting about him. Besides his domain restriction. And now for the funky ones. Look, and we're done. Now for the funky ones. Just don't worry about the step in the absolute value quite yet. We'll get to him in just a second. First of all, let's talk about a piecewise function. You guys have seen this 2 times now. You saw a piecewise function in your graphing calculator handbook, right? very last thing that we did, graphing in the calculator piecewise. Then you saw piecewise functions when we had function notation. Plugging in like f of 1 and f of 5, having to determine which piece you were supposed to plug into. Is there any limitation to how many pieces a piecewise function might have? Super interesting project. I've never actually had time to do it, always wanted to. It's technically more of an Algebra 2 project, but it works in HPrecalc. Is to have you guys define one humongous piecewise function that makes a picture. And I would imagine, from what I've seen of others who have done a project similar, that you might have up to 50, 60, 75 different pieces. Little semicircles here, little lines there, little this, that, and the others all over. In order to make some sort of picture that you would want to make, using a program like Desmos or something, where you take different pieces with different restricted domains, because you don't want all these parabolas and lines and circles and semicircles and hyperbolas. You don't want all of those put together with the entire function to make a picture. You want little pieces of them. Anyway, so piecewise function, you can have all sorts of different pieces. But for right now, the ones that you'll mostly see probably have 2 to 3. I'm going to do 3 just for the heck of it. I'll do g of x, h of x, and j of x. You guys should know why I'm not doing I of x. But we've talked about it. And this one could be something like x is less than a. This could be something like x is equal to a. This is something like x is greater than a. Could be more exciting than that, like x is in between a and b. X is in between b and c. X is in between c and d. You can show up different ways. Long story short, you have multiple different pieces. Can I say, for piecewise, exactly what it's going to look like? No, what's it dependent on? Yeah, the pieces you use. What if you use all linear pieces? Well, they're little segments of lines. What if you use all curved pieces? Well, they're all going to be little different curvatures. What if you use, well, we'll stop there. The long story short, it depends on the pieces. So I can't tell you what's going on as far as the shape. I can't tell you what's going on as far as the branches. What I can tell you is that with piecewise functions, discontinuities, which we'll talk more about later on this year, are possible at x equals the separators. Oh, maybe I did one of these. That's okay. I was going to make a new piecewise, but we'll just wait. Separators, by separators I mean whatever values are used in the inequalities. And this one I just used A. I was kind of boring. I'm sorry. But if I'd used like A and B and C and D, then there could be lots of different separators. Discontinuities, maybe you remember these are things like holes, vertical asymptotes, breaks in the graph, or like jumps in the graph.